Okay, we are going to solve a pretty difficult differential equation, differential calculus problem. Most of the difficulty is going to be concentrated in this dude down here. Part A is going to be pretty routine. Part B, a little bit less routine, but then part C is going to be quite difficult. Let's get started. We have our function k times square root of x minus ln of x. The first task is to find the first and second derivatives. What I'm going to do is right off the bat, write this as a power of x instead of square root of x. So it's going to be k times x to the 1/2 minus ln x. This is just so that it can more easily apply the power rule. So in problem A, f prime of x, just working one term at a time, take the power rule, apply it to this, the 1/2 will come down, and then this will decrease by 1. So this will end up with k over 2 times x to the negative 1/2, and then the derivative of ln x is 1 over x. Although I'm going to write it as x to the negative 1, so as to make it easier to apply the power rule, especially to get the second derivative. Okay, we have the first. Let's get the second. F double prime. Now both parts can be gotten by applying the power rule. Take the negative 1/2 out. That will become negative k over 4 because it's multiplied by negative 1/2. X is now raised to the negative 3/2 power. And then take the negative 1 down. This becomes a plus x to the power no longer of negative 1, but of negative 2. Okay, bingo. This is our second derivative, and this is our first derivative. Part B. For what value of the constant k does f have a critical point at x equals 1? For this value of k, determine whether f has a relative minimum, relative maximum, or neither at x equals 1, and justify your answer. Before we dig into this, I want to go back and discuss, just very briefly, the implied domain of the function f. Specifically this part right here. We know that ln can only accept positive numbers. It can't accept 0. So this gives it an even stricter domain than the square root function, which can accept 0. But other than that, it has the same domain as ln. So this has an implied domain of x strictly greater than 0. It can't be 0 because you can't plug 0 into ln. So when we go hunting for critical values, critical points, we can only pay attention to strictly positive values of x. We don't need to worry about 0. That's going to pop up later on when we do the number line to look at the plus minus behavior of the first derivative. So we know that the critical point will occur at x equals 1. Well, that means at x equals 1, f prime of x equals 0, or f prime of x is undefined. But when you look at the equation for f prime of x, I'll just say f prime of 1, because that really is what we're talking about. F prime of 1 is going to be k over 2 times 1 to the negative 1/2. Well, 1 to any power is 1. So we don't really need to write it that fancy. It's just k over 2 times 1. And then minus 1 to the negative 1/2, or 1 to the negative 1, rather. Well, guess what? 1 to any power is 1. And so really that's just the number 1. Now, examine whether it's possible for this to fail to exist, or whether we have to set the derivative equal to 0. Obviously, this is going to exist because plugging in 1 does not cause any problems with the negative powers. So the only way for this to be a critical point is if this is equal to 0. We don't have to cover the case where it doesn't exist. This is a simple equation. K over 2 is now equal to 1. And then K is equal to 2. So this is part 1 of that answer. So for what value of the constant k does f have a critical point at x equals 1? We found it, but there's more. For this value of k, determine whether f has a relative minimum, relative maximum, or neither at x equals 1. So this answer would get you most of the points for this. Say that we do f prime of x versus x on the number line. What we have shown, and this is specifically for k equals 2, in which case I suppose I should write the formula for it. So if k is replaced by 2, then this will be just 1. 2 over 2 will be 1. So it'd be x to the negative 1/2 minus x to the negative 1. And I'll maybe squinch that just a little to get some more room. So here's our number line. We want to determine the behavior of the derivative on either side of this critical point, right? That's how we see whether it's a max, a min, or neither. At 1, we know that the function is 0. Well, now we need to plug in some sample points. It's tempting to go negative for this. It's tempting to plug in 0 for this, but keep in mind those are outside the domain. So the only valid testing point right here would be some fraction between 0 and 1. The quote-unquote most natural choice to make would be 1/2, because after all, that's like the simplest fraction. But look at this. We're taking a square root of this, right? So x to the negative 1/2 means you take the square root and then do 1 over that. So taking the square root of 1/2 is kind of messy. Taking the square root of 1/4, 1/4, that's better. So we're going to plug in x equals 1/4. So what is f prime of 1/4? We're going to have 1/4 square root it, and then do 1 over that. One-fourth to the negative 1/2 minus 1/4 to the negative 1. The square root of 1/4 is 1/2. 1 over 1/2 is 2. So we see that this is going to be 2. That's from the first term here. And then minus 1/4 to the negative 1, you simply invert it, and this becomes minus 4. Now this is negative 2, right? So that means that over here, it's minus. By the way, you would want to verify that there are no additional zeros. So does f prime equal 0 at any other points? Like, is our number line here not sufficiently thorough? It's easy to verify that this is not going to happen. We know ahead of time that we're not looking for places where it fails to exist. We know that we're only looking for places where the derivative equals 0. Those are the only critical points that are candidates here, because this has a domain that specifically excludes the derivative failing to exist. The domain of the original function is x must be positive, and neither one of these can have any problems if x is greater than 0. So, does f prime equal 0 at any other points? Well, let's see. X to the negative 1/2 minus x to the negative 1 equals 0 is the only case we need to worry about. This means x to the negative 1/2 equals x to the negative 1, which means that x to the 1/2 must equal x. X to the 1/2 is square root of x. And this has two solutions. This says that x must be either 0 or 1. We know that 0 is discounted. We are ignoring that. And so 1 is the only possible critical point, and our number line is not missing anything. So what can we plug in on the right-hand side? We don't need to worry about plowing past any potential future critical points because we know the only one is at 1. So that means that we can pick something as large as we want that's convenient. Well, we picked a 4th for the thing that was to the left. Now for the thing that's to the right, we're going to pick 4 because it has a convenient square root. So over here, we'll plug in x equals 4. So f prime of 4 is going to be 4 to the negative 1/2 minus 4 to the negative 1. What is that? The square root of 4 is 2, and 1 over that, to make it negative, the negative power, is 1 over 2. 4 to the negative 1 is 1/4. So it's a half minus a quarter. This is positive, right? So that means that on this side, it's positive. Now look at this sort of behavior right here. We can see that it must be a relative minimum because the function used to be decreasing. Its derivative used to be negative, but then afterwards it has switched to a positive derivative or increasing. So that means it must have this sort of graph. Just basically, just go down and then back up. That means this is a minimum. So at k equals 2, there is a relative minimum at x equals 1 when k equals 2. And this is the next part of that answer. Okay, now on to the really tricky part of this question. For a certain value of k, the graph of f has a point of inflection on the x-axis. Find this value of k. Now, I want to examine what a point of inflection means, and we also need to use the fact that the point is on the x-axis. Okay. What color? There we go. We'll start a new page because this is going to be long. All right, just get the formulas down. Again, f of x equals, let's see, k times x to the 1/2 minus ln x. And we're interested in an inflection point, which means that we're worried about the second derivative. So I'm going to copy the formula we got for the second derivative from earlier. K over 4, that's a terrible k. K over 4 times x to the negative 3/2. Oh, hang on. That was supposed to be negative, wasn't it? Yes. Details matter. X to the negative 3/2, and then it was plus x to the negative 2. All right, great. For inflection point, this happens when f double prime changes sign. First of all, just like with the first derivative and the generation of a relative maximum or relative minimum, this can happen when either the second derivative is equal to 0 or when the second derivative fails to exist. Those are the times when this can take place. For this function, it should be clear that for the same reason as with the first derivative, where, oops, I don't have the first derivative, but remember the first derivative, we saw that going hunting for a critical point depending on the derivative failing to exist was going to be unsuccessful because in the domain of this function, there are no points where the derivative fails to exist. Similarly, in the second derivative, think of the domain of the original function. Its x is strictly positive. This will not fail to exist at any point in the domain. So you can like expand your entire search. You don't need to restrict yourself to like, oh, well, is it equal to 0 or does it not exist? Because you're guaranteed that at all points in the domain, the second derivative will exist. That means we're looking only for f double prime to be equal to 0. Now I want to look at the condition that says on the x-axis. This is a little bit trickier. This means that at some point on the function, you must be at x comma 0. Think about y. On the x-axis, the y-coordinate must be 0, right? So what this means is that for this x, f must be 0. So we must have the original function equal to 0, and we also must have the second derivative equal to 0 at the very same point. We don't know what the x is. Notice that it's not specified, but we do know that the function must be equal to 0. So I'm going to put this information into the original. So the second derivative must be 0. I'll copy down the equation that implies. Negative k over 4 times x to the negative 3/2 plus x to the negative 2 must be equal to 0. Well, I also have a second equation, and that is that the original function must be equal to 0. K times x to the 1/2 minus ln x must likewise be equal to 0. Notice that this is a system of equations. There are two variables here. There's x, which is unknown, and k, which is unknown. But if you have two equations with two variables, you can find an answer. The way to do it is a little bit difficult to see, but it's based on factoring the first of these two equations. What if you take out or factor out x to the negative 2 from the left-hand side? So on the left, that means we're going to be looking at x to the negative 2 times. Now, this is weird because you don't usually think about factoring something like this, but it's negative k over 4 times x to the what power? What power would be necessary here in order for the expanded version to get back the negative 3/2? Well, negative 2 plus this power, whatever it is, must be able to get us the negative 3/2. That means that this power must be 1/2. Think about what this would get. Think about it for a few seconds. What's negative 2 plus 1/2? It's negative 3/2, isn't it? The reason you want to take out x to the negative 2 is that now this is going to be 1. Okay, now stop and think about it. You've got a factored equation where it's equal to 0. Think back to pre-calc or maybe even just algebra. Whenever you factor something and you set it equal to 0, you know that one of the factors must be 0, right? That's the only way for this to have a solution. But looky here, x to the negative 2 can never be 0. It's 1 over x squared, right? That's what x to the negative 2 is. That can never be 0 because the top of the fraction can never be 0. So if this is going to have an answer, this must be 0. Okay, now we're getting somewhere. So if that must be 0, then really the two equations that we were dealing with originally turn into this. It used to be like equation number 1 and equation number 2. If we rewrite them with the same solutions, it'll be equation number 1 will turn into negative k over 4 times x to the 1/2 plus 1 equals 0. We didn't do anything to equation 2, so I'll just copy. K times x to the 1/2 minus ln x equals 0. What I'm going to do is turn this into an equation that is purely in terms of k. Because if it's just in terms of k, then I can solve for that single variable. I'm going to take the first equation, equation number 1, and isolate x so as to substitute it into the second one. This is going to move fast. if I move the 1 over to the other side and multiply by -1 on both sides, I get a +1 on the right, and the left has become positive as well. Now I'm going to isolate the x by multiplying by 4 over k. See how that's going to get rid of the fraction on the left. So x to the 1/2 power equals 4 over k. And now I'm going to square both sides so that x is really just by itself. Although, no, wait, you're a grown-up. We don't have to do that. Look at the fact that x to the 1/2 is isolated, right? Well, I could square it, get x, and then substitute that in here. But if you really examine it, it's already x to the 1/2 here. So why not just swap this in directly? See what I mean? Oh, all kinds of tricks going on here. So we're going to take the x to the 1/2 version of 4k. Boop, 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 boop. And we're going to say, sub this in for x to the 1/2. Because we are very sneaky. And let's take the x to the 1/2, turn it into 4 over k in the second equation. And the really cool thing is, when we do that, we're going to get an equation that's purely in terms of k. So, or wait, I'm sorry, purely in terms of, well, we'll see. We'll see. It's going to be cool. Don't worry. So we're going to take the x to the 1/2 and replace it with 4 over k. So that will mean k times 4 over k minus ln x equals 0. Notice, I'm being strategic here. I want to turn this into something in terms of k, but this x I actually left alone. Okay? So let me think. Is that the best case? What do we want to solve for? For a certain value of k, yeah. Okay, so we do want to solve for k itself, which means the smart-ass way is not the most efficient way. So we'll also get that this says x equals 16 over k squared. So this right here, this x thing, this is going to be converted into 16 over k squared. All right. Usually, if you have a variable both inside and outside of a logarithm, you're stuck because there's no way to make those like actually solve one another without using Desmos or a graphing calculator. But the cool thing about this is that the k on the outside goes bye-bye. So really, the k on the inside of the log is the only thing you have to worry about. Notice that? It's very nice. So this tells us that 4, that is all that's left in that cancellation. And now I'm going to apply laws of logarithms. Minus ln 16 plus ln of k squared. Remember that from last year when you took pre-calc? Laws of logs can expand this. And furthermore, this can be turned into 2 ln k. Because the exponent can be taken outside. This equals 0. The minus sign goes through the parentheses, and then I'm going to rearrange as well to get 2 ln k, which is negative. I'm going to get that by itself on the other side. And on the right side, there's going to be the negative ln 16. I'm going to add that to both sides, so that'll be positive. And then this gets subtracted from both sides, so that's negative. I now want to get ln k by itself. That means I'm dividing by -2. Divide by -2 means what used to be minus is plus, what used to be plus is minus. So I can say this is, instead of ln 16 minus 4, it's 4 minus ln 16. Notice how that takes care of the minus sign part of it. divided by 2. Almost there. Another property of logs is that every equation that can be written as a log can also be written as exponentials. So this says that k must be equal to the power, e to the power of 4 minus ln 16 over 2. Like that entire thing is the power on e. Now, what we've shown here so far is that this is the point, or this is the value for k that will cause there to be the second derivative equal to 0 on the x-axis. What we haven't shown is that it is an inflection point, because sometimes the second derivative being equal to 0 doesn't guarantee the existence of an inflection point, because although it's equal to 0, it doesn't change sign. It's just like the first derivative can result in either a relative minimum if it goes from minus to plus, a relative maximum if it goes from plus to minus, or neither one, if it's positive 0 for an instant and then back to positive, or negative 0 for an instant and then back to negative. The second derivative can do the same thing. It can fake you out. But you've already watched this super long video, and I bet that now you just want to be done. See if you can work it out for yourself. Try using this value for k and work out whether it's a legitimate inflection point or whether it's just one of those strange ones where the second derivative equals 0, but is either positive on both sides or negative on both sides. After all, I mean, I got to leave some of the fun for you, right? That's what life is about.